Hey everybody! So we are going to just pick up right where we left off last time with our notes, and I just wanted to just review what we had talked about last time. So when we were starting chapter 9, we're looking at testing a claim. We're doing our first batch of significance tests. Now last time we just did some definitions and kind of described what was happening. We learned about how to write our hypotheses, how the null hypothesis is always a statement of no difference or no change or effect in the population parameter. The alternative hypothesis is our competing claim. We always write the hypotheses with respect to parameters, never statistics. And the hypotheses should express our hopes or suspicions before we've collected the data. Now remember that there's two reasons for things to be happening. So you have a sample value. So like for example, remember this one we were talking about the golf and Mike and golfing. So the null hypothesis was looking at the standard deviation to be 15. He has a sample mean of 13.9. So if he has a sample mean of 13.9, does that mean that sigma is equal to 15 is wrong? Well, the answer could be maybe. So there's one explanation is that the null hypothesis sigma equals 15 is really correct, and we just got this sample value that's low by chance. Or this could be evidence that the null hypothesis isn't true, and that means that the alternative is really true, that sigma is less than 15. So just like with confidence intervals, we're not going to ever know if what decision is correct. We're just going to use probabilities and what we know about, good, sound statistical practices in order to help us use probabilities to make some decisions. But as with all decisions, you have some errors that are possible. So we take our p-value and we either reject or we will fail to reject the null. It depends on the p-value's relationship to alpha. If the p-value is smaller than alpha, then we reject the null, and if the p-value is greater than alpha, then we fail to reject the null. But then again, there's errors that can be made. So we can have what's called a type 1 error or a type 2 error. So type 1 error is when we reject the true null. So the null is really true, but our p-value is so small that we end up rejecting the null hypothesis. And the opposite, a type 2 error, is that you fail to reject a false null. So there's this little box that you can create to help you remember which one's which, or you can just memorize this part, rejecting a true null. This is a type 1 error. And fail to reject a false null is a type 2 error. So I know that 4th period did this example, but 6th period didn't, so I'm just going to cover it for everybody again. So here we have the U.S. Department of Transportation reporting that during a recent period, 77% of all domestic passenger flights arrived on time. Suppose that an airline that has a poor on-time record decides to offer employees a bonus if the airline's proportion of on-time flights exceeds the overall industry standard of 77.77. Describe type 1 and type 2. Okay, so the null hypothesis is that there is no difference from the claim. So the claim is a 77% success rate, and we're looking at exceeding the overall industry rate. So the alternative is p greater than 0.77. So if we can exceed the industry rate, then we get a bonus. And so I want to make sure to define what p is, where p is the true proportion of on-time flights for this airline. Okay, so type 1 error means we reject a true null. Okay, so I like to do it this way, and I know it's kind of formulaic and weird, but bear with me. Okay, so if we reject a true null, in context we want to write down like what we think is happening when really something else is happening. So we're rejecting a true null in favor of the alternative, right? Whenever you reject a null, you're in favor of the alternative. So that means that we think that the true proportion of flights is greater than 0.77. I would want to put that in words too. The true proportion, well, I mean, even in a more general way, if P is greater than 0.77, that means that there's been an improvement. In terms of online flights or on-time flights. But really, P is equal to 0.77. So when really there hasn't been any improvement. Okay, so then the type 2 error is just the opposite of this. So type 2 is we fail to reject a false null. So we think, so we're failing to reject. We think that P equals 0.77 when really, P is greater than 0.77. Okay, so this is terrible, terrible modeling for you. You would want to put this in context. You think that the proportion of flights has been is still equal to 0.77, but really the airline has improved their on-time flight arrivals. So we think no improvement when really there is. Okay, now you also want to talk about consequences. All right, when you describe consequences, you want to, you don't want to just restate what's happening. You want to really talk about, monetary consequences and what are the consequences of the population of interest, right? So we're looking at the proportion of flights for this airline. So in terms of the airline, if the airline thinks there's been improvement when really there hasn't, so the consequences on the AP exam, you can have a wide variety of consequences that you state, but you really want to make sure that they're really this is a reason for this happening. Okay, so if I think that there's been an improvement when really there hasn't, the company is going to lose some money. So what's going to happen is they're going to give the bonus when really they shouldn't. So employees are happy, but the company is essentially losing money. Additionally, let's think about this in a real world context. If the company thinks there's been improvement for an airline that's traditionally been having a poor on-time record, they might put a bunch of money into new advertising in order to, boost sales or boost plane ticket sales. And so they're putting all this money forth to, say, we're so great, we've made this big improvement, and really they haven't. So they're selling themselves, but they're not able to live up to the challenge. And so I think in the long run, they're going to lose some credibility because they're false advertising. So you can describe those consequences in a lot of different ways. You would say something like employees get an undeserved bonus. Customers are unhappy. They lose credibility in terms of the airline. And overall, they lose money. Now, type 2 error. So in this one, they think that they have had no improvement, but really they have. And so, let's see, employees are going to be bummed because maybe they worked their butt off and they really have improved, but they're not getting their bonus. So they don't get a deserved bonus. And that can trickle down in a lot of different ways. So the employees are disgruntled, so then they're not being as friendly, and eventually that may trickle down into customer relationships and so on. This is also a lost opportunity. Oftentimes type 2 errors are lost opportunities. And you want to make sure that you describe, like you're always going to be asked to explain the consequence, and so you want to really explain, like pick one. You don't have to name all of these. You want to pick the best one that you think is the most applicable, and you want to just describe it. Okay, I'm giving you lots of options here so you know that there's lots of different possibilities. So if it's a lost opportunity here, this means, no new advertising, which equals no new customers. So they have improved, but they're losing the opportunity to really take advantage of that and make some money for the company. Okay, so so while you have some probabilities here, when you set a level of significance, you're setting the probability of making a type 1 error. So up here, remember how we said what should be considered when choosing a significance level? Well, what are the consequences of rejecting the null hypothesis? If the consequences are slight, then making a large value of alpha is going to be just fine. But, if there's a life and death situation, then you probably want to have a really small value of alpha. And so we're going to practice that as we go through here. Now, the probability of making a type 1 error, as I just described, is alpha. So the probability of a type 1 error, it's actually a conditional probability. It's the probability that we reject the null hypothesis given that the null hypothesis is true. So this is alpha. It's our level of significance. So how do we reduce this error? So to reduce this error, we demand that the evidence be very convincing before rejecting the null. So that means we make it a small value. So we make it be 0.01. And so that means that my p-value has to be smaller than that. So that means my evidence has to be really, really convincing in order for me to reject the null. It has to be super duper far away. If this is the null hypothesis and here's my p-value, or here's my p-value, I want it to be really, really small. I want my my statistic to be far, far, far away from the null hypothesis so that I'm going to make sure to reject it. Making it harder to reject, however, means that you're more likely to make a type 2 error. So we're not going to get into the relationship of type 1 and type 2 quite yet. So if you're feeling a little uncertain about, what this all means, not to worry. We're going to get today into actually performing some significance tests and seeing the numbers and how the numbers are reacting with each other. And then we will go back and take a look at error. Okay, so today we're just finishing up here what we didn't finish last time. And then we're going to get into the significance test for a population proportion. And then on Tuesday, we'll talk more about the errors and power and how type 1 and type 2 all play together. Okay, so here I have just one little example practicing type 1 and type 2. So it tells us that there are some communities where tap water has too much lead. Lead is dangerous for your body. So drinking water is considered unsafe if the mean concentration of lead is 15 parts per billion or greater. So the EPA requires the cited communities to take corrective actions. Let's identify the parameter of interest. Okay, so we're talking about means here, the mean concentration of lead. So let's let mu be the true mean lead concentration in tap water for these communities. We want to state a null and alternative hypothesis. Okay, so this one's tricky. So we have mu equals to 15. So it's considered unsafe if it is 15 parts per billion or greater. And so here's the big question, is how do we set up the alternative hypothesis? Do I want it to be less than, or do I want it to be, or do I want it to be greater than? Okay, so we want to make sure that these hypotheses are really like diametrically opposed. So if I'm equal to 15, is that bad or good for the water? It's bad, so the water is unsafe. Bad water. Okay, but so then think about the two alternatives here. If the mean concentration is less than 15, is that good water or bad water? That's good water. If the mean is greater than 15, is that good water or bad water? That's still bad water. So this is not how I would set up the hypotheses. I'm going to set it up this way, where the mean is equal to 15 and the mean for the alternative is less than 15. Remember that this symbol in the null hypothesis is really the other side of the inequality. This really means greater than or equal to, but we don't write it that way. You have to know that that's what's going on in the background, but the convention is to write an equal sign here. So the null hypothesis is representing bad water, and the alternative, that's our hope. Our hope is that we're going to have good water. So our hopes or suspicions are the alternative. So type 1 and type 2 error. All right, so type 1 error is to reject a true null. So I'm going to reject the null and go with the alternative. So I think that the mean is less than 15 and that the water is good. But really, the null is true. Mu is equal to 15 or greater. So the water is bad. So, what kind of consequences is this? I think the water's good. So the they're gonna, let's see, the EPA, I don't know, let's say the water community is deciding whether or not they're gonna approve water drinkage or not. So the water district thinks that the water is good, but really the water is bad. So they're gonna say, oh no, the water is good, go ahead and drink it. So people are going to drink some unsafe water. That's kind of bad. If you have too much lead, you can get lead poisoning, which equals death. So kind of a problem. Type 2 error. This means fail to reject a false null. So we fail to reject the null. We think that mu is equal to 15, that the water is bad, when really the mean is less than 15, meaning the water is good. So we think the water is bad when really the water is good. Okay, so this is again kind of a lost opportunity. So what's going to happen is if we think the water is bad, there's going to be more money spent on more tests, more analyzing. People will buy bottled water. I guess you could take it further. Like, people are going to buy more bottled water, and then it's going to be more plastic pollution. Like, don't go crazy. Just talk about this context. So people are going to spend more money, and they're going to... it's going to be expensive. They're going to spend a lot of money to clean up the water, to test the water, to find alternative water sources when it's unnecessary. So customers or community That's an O. So yeah, expensive to clean the water, maybe replace current water pipes, spend money to find an alternative water source when unnecessary. Is that two N's? I don't know. I don't think so. Okay.